Welcome to the Chemistry 223 lab with the longest name of all the classes, I think. But anyway, the lab is the determination of Ksp, delta G, delta H, and delta S for calcium hydroxide. And it's kind of a cool lab, a lot of little pieces in there. We're going to pull all this thermodynamic stuff together. But anyway, I'm glad you're here and let's talk about it. In this lab, the ultimate goal really is to find values for delta H, the enthalpy, and delta S, the entropy for calcium hydroxide. We're going to use a couple of temperatures to find these, and in these ranges, the delta H and delta S terms should be constant. So finding the enthalpy and entropy, the delta H and the delta S are the key parts, the holy grails. The little zero means it's standard conditions, and usually standard conditions for these, as I said, are pretty constant. Now, in order to do that, we're going to use the solubility of calcium hydroxide. And solubility is how many moles per liter of calcium hydroxide dissolve in water at that particular temperature. And we're going to find the solubility at two temperatures. Now, calcium hydroxide is a 1 cation to 2 anion system. Like it breaks down to calcium 2 plus and 2 hydroxides. And like we saw in lecture, if this is a 1 to 2 system, the equilibrium constant for solubility, Ksp, aka solubility product constant, Ksp equals 4 times the solubility to the third power. So if you know the solubility, which is just so many moles per liter of calcium hydroxide that's dissolving in water at that temperature, if you know that solubility, you cube it and multiply by 4, and you'll have the Ksp, which is pretty cool too. Now, Ksp, you can convert into a delta G, a Gibbs free energy. And Gibbs free energy, delta G, little standard conditions, equals minus RT natural log of Ksp. So we'll use that Ksp from the previous one, take the natural log of it, Ln. We'll also multiply by minus RT. R is what I call the energy gas R. It's the 8.3145 joules per mole Kelvin number that we've used several times. And T is the Kelvin temperature. So because we have two solubilities at two temperatures, you can see here now where the temperature term is coming in. So you'll have 2 Ksps and 2 delta Gs. And finally, once you have the 2 delta Gs, we can use algebra and figure out what delta H and delta S are using those things. So remembering that we have 2 delta Gs and 2 temperatures, we can plug those in. We'll have 2 equations. We'll solve first for delta S and then for delta H. It's pretty cool. And yes, I will give you an example in a little bit, so don't worry about it. Let's go back and talk about some of these a little bit more here. So calcium hydroxide, all right, the Ksp expression, it's always the solid on the reactant side and the ions that go into it on the product side. So calcium hydroxide solid is in equilibrium with calcium 2 plus aqueous plus 2 hydroxides. This is the 1 cation and 2 anions I mentioned earlier. So 2 hydroxides and 1 calcium come out of calcium hydroxide. And Ksp, when you figure it out, Ksp, the solubility X, X and calcium 2 plus are the same, but hydroxide, there are 2 hydroxides per solid calcium hydroxide. So in the middle part for hydroxide there, the OH minus, you'd have 2X. And again, because in equilibrium concentration calculations, the stoichiometry is the power, it would be 2X quantity squared. So long story short, Ksp equals 4X to the third power, where X is the solubility. Now again, don't be confused by this. Remember, the X is just how many moles per liter of that solid are going to dissolve in water at that particular temperature. And if you know that solubility X, X cubed times 4 is going to give you the Ksp part. Now, once you have that, if you want to find solubility, it's not too hard. We're going to titrate it. And titrations, we've done a lot of already. This will be our last titration lab. We're going to titrate calcium hydroxide, a base, a pretty strong base, by the way, with hydrochloric acid. And hydrochloric acid, a strong acid, is going to react with calcium hydroxide to make calcium chloride and 2 waters. Notice that there's a 2-to-1 ratio right there. And that's going to be important to us here in a little bit. So if we want to find the solubility X, all right, and we've done this titration to the endpoint, if we know at the bottom there, you can see the molar concentration of HCl, and we multiply it by the volume of HCl used, that's going to give us essentially moles of HCl. We need to convert moles of HCl into moles of calcium hydroxide. We have to divide that by 2, and you can see there's a little 2 in there. Anyway, if we do that, that'll give us the moles of calcium hydroxide. We divide that by the volume of calcium hydroxide. That's going to give us the solubility. So either by plug and chug or by looking at these, you can see how these all are going to interact and what's going to happen. So this will allow us to go from a titration where we'll have a volume of HCl added and the volume of calcium hydroxide and molarity of HCl, et cetera, we'll turn all of that into the solubility, and that's going to be kind of a cool thing here in a little bit. So in this lab, we're going to use HCl through the use of an indicator, a thing that turns color, and I'll show you an example of this. Now, because these are going to be short and sweet titrations, we're going to do 3 trials at each temperature. So you're going to have 3 trials of this titration at about room temperature and 3 trials at a warmer temperature, and from there you can average them and all that kind of stuff. We'll find the average solubility at each temperature and calculate parts per thousand. Parts per thousand is a great way to show how close your measurements are to each other, and hopefully they should be pretty small in this lab. Once we have those solubilities, those X values, you can put that into Ksp. And again, solubility to the 3rd power times 4 is equal to Ksp for this lab. Now remember, in all of these parts so far, there's 2 interesting parts. There's 2 temperatures, and each temperature will have its own average solubility. Each temperature will have its own parts per thousand, and now each temperature is going to have its own Ksp as well. So remember that as we go through all this jazz. After you have the 2 Ksp values at the 2 different temperatures, you can use the delta G equals minus RT natural log of Ksp to find the Gibbs free energy values, delta G. And remember the R is 8.3145, the so-called energy R value, joules per mole Kelvin. And T, like all the temperatures in this lab, basically will be, at least in calculations, in Kelvin. So if you do that, you can turn your Ksp into a delta G, and you'll have 2 values of delta G once again, one at the lower temperature and one at the higher temperature. So the last part now is just to find those enthalpy and entropy values, the delta H and delta S. And we'll use the Gibbs equation to do that. But the problem is we have delta G and T, but we don't have delta H and delta S. Fortunately, we do have delta G and T at 2 different equations. So we've got here a way we can write this out. Notice I have a delta G cold and a delta G hot. The delta G cold equals delta H minus T cold times delta S, and delta G hot equals delta H minus T hot delta S. So what we can do is combine these 2 equations. We'll cancel out delta H by subtracting like the second equation from the first equation. We can then find delta S, and from delta S we can plug them back in to find delta H. And if that is about as clear as molasses, let me show you an example which I think will be more helpful. Here's an example. Let's find delta H and delta S using a delta G of 19.9 kilojoules per mole at 273 Kelvin, and also a delta G of 0.0124 kilojoules per mole at 298 Kelvin. So we have a cold 273 and a hot 298, and again those are very arbitrary, and you can see how the 19.9 number goes with 273 and 0.0124 goes with 298. So like we did on the last slide, we're going to have a delta G hot and a delta G cold. So the quote-unquote hot is the 0.0124, and that equals delta H minus 298, the hot temperature delta S. We also have a cold delta G, which is the second equation, 273 being colder than 298. So 19.9 equals delta H minus 273, the temperature, times delta S. And at this point, what we're going to do is we're going to subtract equation 1 from equation 2. So it's like the hot minus the cold. And when you do that, you can see here how you've got the 2 delta G values, 0.0124 minus 19.9. So again, we're subtracting the second one, and that equals delta H minus delta H. And of course, that's the same, so it goes to 0. And then over on the other side, we've got minus parentheses, hot minus cold, 298 minus 273 delta S. So again, this part goes to 0, so we don't have to worry about that. 0.0124 minus 19.9 by sig figs, cut it off at the 10th, is minus 19.9. And over here on the right side, 298 minus 273 is 25, but don't forget that negative. So it's like minus 25 delta S. And to figure out what delta S is, you go minus 19.9 divided by minus 25, 2 sig figs, 0.80 kilojoules per mole is the delta S. And notice how the value of delta S is a kilojoule per mole because both of our delta G's were kilojoules per mole. You want to keep using the same units. Now to find delta H, you can plug it back into either equation, either the hot one, which is what I'm going to show you, but you could also do it for the cold one, the 19.9. So I'm going to use the hot one here. So you can see that this equation right here is just like the first one up here. It's 0.0124 delta G equals delta H, which we don't know, minus 298 times the delta S we saw earlier. And so minus 298 times 0.80, you want to add that to both sides to get delta H by itself. Delta H equals 0.0124 plus 298 times 0.80, delta H here, 240 kilojoules per mole. Now, you should get that exact same answer if you plug it into the cold equation. And this is a good thing to practice. If you put 19.9 equals delta H minus 273 times 0.80, you should get that same answer. Try it and see that you do. So in this lab, you're going to do a total of 6 titrations, but they're all really short. Most of the time, the total volume you use from the burette is less than 5 milliliters. It's pretty fast. You'll do 3 at the cold, quote unquote, temperature, which will probably be room temperature for you, and 3 at a warmer temperature, which will be closer to 100 degrees Celsius. Probably not 100, but closer to 100. Then you'll average them like we talked about. You'll find the solubility. You'll turn solubility into delta G for both temperatures, and from that information you can find delta H and delta S. So again, you can write all this data in your worksheets and then work on it later at home if you'd like. Show example calculations of how this works out, and then you'll turn it in to me the next time we meet in lab. If you have any questions, of course, reach out to me. I know this can be a little weird, but it's a pretty powerful technique, and you can find entropy and enthalpy for these kind of situations, which is really cool. Just kind of go with it and see what you find. Okay, at this point, I'm going to show a quick video that shows what the lab will actually be like. It shows some setups and the titrations. They go pretty fast, like I said. It's a lot different than the other labs we've done. If you have any questions, again, reach out to me. I'm happy to help. You can also talk to the LSC Avid Center. They're also there to help as well, so there's lots of people ready to assist you if you need it. All right, good luck with the lab, and thanks for being here. Let's watch and see what the lab is going to be like.